Welcome back to Elementary Statistics. In this video, we're going to start our discussion of central tendency with the average. I've mentioned the idea of central tendency a couple of times in previous videos, but formally I can define it here as an explanation of how the data are behaving on average. It's a bit of a vague definition because there are several different ways we can approach this question, which are useful in different contexts. The first one we want to talk about is the mean, specifically the arithmetic mean. There are several different meanings of mean that can show up, and the arithmetic mean is the one that is being referred to if you hear somebody refer to mean on its own. And the arithmetic mean is the tool of average that you've learned since grade school. Add up all of the scores that you have, divide by the number of things that are there, and that gives you the average. We call that version of average the mean, or more specifically, the arithmetic mean. Let me get my head out of the way. Let's go through a relatively trivial example just to get some notation out of the way. Oh, before I do that, I've already gotten ahead of myself. We've talked about these ideas previously. A statistic is a characteristic attained using data from a sample, while a parameter is a characteristic which is obtained using data from the entire population. When it comes to talking about the mean, this is important because statisticians use a different variable to describe the mean of a sample or the mean of a population. The mean of a sample is written as the variable, which is usually x, with a bar over it, and it's read simply as x bar. The mean of a population is written using the Greek letter mu, which kind of looks like a curly M or a U with an extra long tail, depending on how you want to look at it. Right? It is supposed to be an M, but it looks more like a U. You may have come across this symbol in the past if you've taken coursework in the natural sciences. You might have ended up using micrograms or micrometers. And this is the SI prefix for micro is represented using the symbol mu. Right now, it's going to feel like excessive complication just for the sake of complication. The calculation of a mean works the same whether it's a sample or a population data that you're looking at. But remember again the purpose of statistics. Our goal is always to collect a sample, calculate some value for the sample, and use that sample to predict what the value for the population is. So for right now, it is notation for the sake of notation. It's confusing. It feels pointless. but it is going to be important in the future. One of the most important things we're going to look at in this course is going to come about halfway through the semester, where we find a formula that is going to take the mean of a sample and the mean of a population and put them in the same formula. And given information about the mean of the sample, it will allow us to say things about the mean of the population. So it's important that we have different symbols for each of those. It's important that you get used to using different symbols for each of those so that it makes sense to you when it comes up later on. And now that we have those symbols, and now that I can push the right button, we can look at the formula. And again, it's the same formula either way. I've been using the convention that capital letters represent data from a population and lowercase letters represent data from a sample. So X bar, the mean of the sample, is written here using the capital letter, Greek letter sigma, which I think I mentioned in a previous video, but it's worth repeating. It is a notation that literally tells us add all of the. So X bar says add all of the little x and then divide by little n. Remember, little n is the number of data values in the sample. For the population, we use a capital X to represent the individual data values, and we use a capital N to represent the total size of the population. All right, so notationally, this feels weird if you've not studied statistics before, but conceptually, again, this is the rule of average that you've known for all of your life. So for example, if I'm looking at a relatively simple distribution, right? I have x values of 3, 2, 6, 5, and 4. I can see very quickly that there are 5 data points in this distribution, so little n is 5. If I want to add these all up, sigma x is 3 plus 2 plus 6 plus 5 plus 4, which is, let's see, 5, 11, 16, 20. And then x bar is 20 divided by 5, which is 4. All right, it's the calculation that you know. The notation, the symbols might be different. Don't let the fact that the symbols are different throw you off. I very carefully chose this example so that when we performed the calculation, we wouldn't have to round anything. That usually doesn't happen. So we're going to use this rule of thumb. However much detail we are given for the raw values in a distribution, whenever we perform a calculation, we're going to go 1 digit further. So as another example, if I get some really ugly numbers here, All right, how about some values of 4.5, 6.3, 9.7, 8.2, 5.4, and 9.1. One more value. 7.7 seems like a nice value to put in here as well. Right. In this distribution, there are 7 scores. If I add them all together, I get 50.9. And if I take 50.9 and I divide by 7, I get a really ugly decimal number. 7.27142857, etc. My rule of thumb says I want to keep one more value than I'm given. All of the data, all the raw data in this distribution was rounded to the nearest tenth. And so one more digit than the nearest tenth is the nearest hundredth. I'm going to round and say that X bar is approximately 7.27. Right. Some of you may have a mathematics background where you have looked at this idea a little bit more carefully. The idea here is known as propagation of error, and there are a lot of different rules of thumb. Sometimes you'll see things involving how the calculation works, how many digits are there in the number in each step of the process, and trying to keep that consistent. You can even get to be a little bit more technical if you want to use calculus for it, but it's just not worth it. So our rule of thumb is very much a simplification. It's intended to make it so that you don't have to think about things and you'll still get a reasonable looking result. So, don't overthink it. The idea is to round so that you're not writing out the 20 digits that your calculator displays. You have to round somewhere. Here's a nice, easy way to figure out where to round. Don't think about it too much harder. This idea of mean really starts to get fun when we start looking at data given in a frequency distribution. To make things as hard as possible, I'm going to jump into a grouped frequency distribution. And let's set up 5 classes. 15.5 to 20.5. 20 and a half to 25 and a half, 25 and a half to 30 and a half, and so on. And then for each of these classes, we have our frequencies, relatively low frequencies here all told. I'm going to have 13, 6, 4, 1, and 1. All right. So first thing, as I've talked about when we talked about grouped frequency distributions previously, because the data was collected in a grouped frequency distribution, we have lost information. Because we have lost information, that's going to affect the calculation of the mean. but it's not going to be all that bad and we can work with it. When we talked about grouped frequency distributions before, I mentioned that finding the midpoint of each class of the distribution was the way to go. And so we're really going to start to see the power of working with statistics in tables and building out the table. You'll see as I build this one out, the general process. But whenever you're looking at a statistical table, generally you want to read the table column by column from the left to the right, because that's how we build it. We start with our class boundaries, then we go back and we figure out the frequencies, and then we start doing stuff. We look at the class boundaries, we use that to find the midpoint. Let me get my head out of the way and let's do just that. So let's extend this table out, put in a new column. I'll call it X sub M for the midpoint of the class. And halfway between 15.5 and 20.5, grab your calculator. 15.5 plus 20.5 is 36. 36 divided by 2 is 18. And then we'll have 23, 28, 33, and 38, just doing the same thing for each of these classes. And now that we have that, we can think about this frequency table, this frequency distribution, as being a set of these scores. There are 13 scores, each of which has the value of 18. There are 6 scores, each of which has the value of 23, 4 scores that say 28, a score that says 33, and a score that says 38. When we create the grouped frequency distribution, we round all of the scores in the distribution to get a manageable number of different scores. I want to find the mean of this distribution, which means I want to add all those scores up. I could list them out and add 18 plus 18 plus 18 plus 18 plus 18 plus 18 plus 18, 18, 18, 18, all 13 times, add all the 23s, add all the 28s, add 33, add 38. It's not that bad for this particular distribution because the total number of scores in the distribution is still relatively small. But I think you can imagine pretty readily that it's going to get a lot worse. And so it's nice to have a couple of tools at our disposal. The next tool I want to look at is finding a subtotal. The basic definition of multiplication is repeated addition, right? If you have 6 times 3, that literally means 6 plus 6 plus 6. 6 added to itself 3 times. And that's what we want to think about here. I have these scores of 18, and I'm going to add 18 to itself 13 times. Why go through and do all that calculation when I can just calculate 13 times 18 and give myself a nice shortcut? 13 times 18 is 234. 6 times 23 is 138. 4 times 28 is 112. 1 times 33 is 33, and 1 times 38 is 38. And so now I have some numbers I can work with. Again, just saving myself from having to add all these things together. This particular distribution is not all that bad. The number of scores in the distribution is the sum of all of the frequencies. 13 plus 6 is 19, 19 plus 4 is 23, 24, 25. All right, 25 scores is not unreasonable. You can put 25 numbers into a calculator and probably not make a mistake. But imagine if instead of 25 scores, there were 250 scores in this distribution. At that point, this shortcut of coming up with the subtotal is going to go from its fine to I'm not going to like this at all. All right, the other thing that we need is the total of all of our scores. And this is where the subtotal becomes so useful because the total of all of the scores that say 18 is 234. The total of all the scores that rounded to 23 is 138. So we just add up all of the subtotals. And I get that this total is 555. Then finally, to find the mean, I take that total, 555, I divide by the number of scores, 25. My calculator is happy to tell me that 555 divided by 25 is 22.2. Right? In this case, that turned out exact, but even if it hadn't, my scores are all rounded to the nearest whole. My midpoints are all rounded to the nearest whole. So rounding my mean to the nearest tenth is the way that I had wanted to go about that anyway. All right. I have one last idea related to the mean that I want to talk about in this video. It's called the weighted mean. And I'm going to show you the weighted mean with an example with grade point average. There's formulas that you can use. I find that looking at the formula makes things more confusing instead of less confusing, so let's not. Um, so let's imagine a student who is taking these 5 classes: world history, algebra, Shakespeare, art history, and chemistry. World history, algebra, Shakespeare, and art history are all 3-credit classes. Chemistry is a 4-credit class because it has a lab. And let's say that this student earned a B in world history, a B in algebra, a C in Shakespeare, an A in art history, and an A in chemistry. Well, the usual standard is that a grade of a B is worth 3 grade points, a C is worth 2 grade points, and an A is worth 4 grade points. To find your grade point average, you don't just average the grades because they are all awarded per credit. So if you have a 3-credit class where you earned a B, that means that you earned 3 times 3, which is 9 grade points for world history and 9 grade points for algebra. 3 times 2 is 6 grade points for Shakespeare. 3 times 4 is 12 grade points for art history, and 4 times 4 is 16 grade points for chemistry. If you add up the credits, 3 plus 3 plus 3 plus 3 plus 4 is 16 total credits. If you add up the grade points, 9 and 9 is 18, 18 and 6 is 24, 24 and 12 is 36, and then 36 and 16 is 52. Right? To calculate your GPA, you take your total grade points, which were weighted by credit, 52, you divide by the total number of credits, 16, the weight of the category. And my calculator is quite happy to tell me that 52 divided by 16 is a GPA of 3.25. GPA calculations are often something that you have tried to do before, so the idea of weighted mean should be something that's familiar to you, right? We take some score that we care about, in this case, the points for each grade, and we weight it by something. In this case, each grade is weighted by the number of credits for that class. Multiply them together to get your subtotal, add those together to get your total, and divide by the total weight of everything. It's essentially the same thing that we did for the grouped frequency distribution. The context is just explained a little bit differently. So calculating the mean of a frequency distribution, calculating the weighted mean of scores that have weights, all fall into the same basic idea. The calculation should feel very similar. It starts to get a little bit messy as to how you're doing it, but the idea should feel the same every time. Pay attention to whether we're talking about a sample or a population. That changes which variable we use to represent that idea. And that's all I have for this video. I'll wrap up here. And next time we'll look at some other tools that we can use for describing the central tendency. I'll see you then.